Hello everyone, welcome to Drawing Hub. This is Sanjana, and in this video we will be continuing with part 7 of Distributed Computing Module 1. This shall be the last part. In the previous sessions, we have already discussed about distributed system basics, the relation to computer system components, motivation for why we have distributed computing, the features of distributed computing, primitives for distributed communication, single send, receive function, then synchronous, asynchronous, blocking, non-blocking, then different versions of send primitive, the design issues, challenges, and applications. And in the last session, we also discussed about model of distributed computation, distributed program, and all. In this session, we will be continuing with models of communication network. If you have any doubts on those topics which I have told before, you can visit and watch my previous videos to get more clarification on those topics. Let's get started. Models of communication. So there are different models of communication network, like FIFO and non-FIFO causal ordering. So what is FIFO? First in, first out. From the word itself, it is understood. There will be a message queue, and the priority will go to the first one which goes inside the queue. It is something like FIFO is something like queue, right? So the message ordering is preserved by the channel in FIFO method. Whereas in non-FIFO model, what will happen is when the sender process adds messages and the receiver process removes message, there is no particular order in it. The receiver will remove it in random order. There is no order in it. But in FIFO, the message ordering will be preserved. Then for causal ordering model, it is based on Lambert's happens before, which we have already discussed in the previous session. So here what will happen is we need to follow the property given here for causal ordering. What is it? There are two messages, mij and mkj. If the send mij happens first and after that send mkj happens, then when the second process, when it receives, also first one will be mij to be received, only then mkj will be received, so that ordering is preserved. They will be delivered to the destination in that same order. That is called causality relation, causal order, and we have already studied that, right? Causal ordering model is used in distributed algorithms, and therefore it provides a built-in synchronization also. Global state, again we have discussed this, we'll just go through it. What is a global state? We know local state. Local states will have processor registers, stacks, local memory, etc. That's all what local states have. But global state will have the local state along with the communication channel. We have discussed it with an example, if you remember. If there is an account for a person P1, the balance is rupees 5,000. I have said the same example before also. If their balance is rupees 5,000, that information is available for that local state alone. No one else is going to know. But in global state, if there is a process P1 or a person P1, and he has an amount of rupees 5,000 in his account, and there is a process P2 or a person P2 where his account he have 3,000 rupees. Then what happens? Then there is a transfer happening between them. That is, the person 1 is sending rupees 1,000 to person 2. Then this is not there in either. This data is not shown in either of the people's account. This is somewhere in the communication channel. It is in a transit mode. So that information should also be included. That is the information in communication channel. That is called global state. So global state is a sum of collection of local state and communication channel. Okay. Okay, that is okay. So channel state, that is dependent on upon the states of processes it connects. So we can write channel state as SCIJXY. We already know what IJ is. IJ is process I and process J. X and Y is event X and event Y. Then also global state, as I've mentioned before, it is a collection of local state of process and the channels. Then comes the most important part of this module, cuts of distributed computation. Cuts, we have already studied what space-time diagram is, right, in distributed computation. So space-time diagram, if there is a zigzag line joining one arbitrary point on each process line, that is cuts of distributed computation. Here we can study that from the figure over here. As you can see, there is four processes are there, right? P1, P2, P3, P4. There are four processes, and in this process P1, look at process P1. What are the events? E1, E2, E3, E4. What is the subscript 1 that is mentioning that this event is of process P1, and the superscript 1, 2, 3, 4, that is the number of event. Now, if you look at the order, we know what is causal ordering. Event 1 occurs first, only then event 2 occurs, then event 3, then event 4. That linear ordering is preserved in it. And again, come to P2. Here also you can see that 1, 2, 3, 4. It is in that order. Again, P3, E1, E2, E3, E4, E5. It is maintained in that order. Now, what is cut? Do you see that C1, a dotted jagged line moved vertically downward in a zigzag manner? Yes, that is cut. Okay, look at the first cut, C1. It is having a left side and a right side. All those events in left side of that cut is called the past, and all those which comes to the right side of the cut is future. Now, so these are past events and future events. Now we have two conditions. We can call a consistent cut and inconsistent cut. How can we say a cut is inconsistent or consistent? We have already know, I have told you this example. When you're telling your friend, you're wishing your friend happy birthday, and the friend replies you back with thank you. So first, what happens over there? You wished your friend. Only because you wished your friend replied thank you. Is it possible your friend first says thank you and then you wish? No, that is not possible. So, consistent cut means if in an event, it moves from past to future. Past to past is possible. You can look over here in process P3. Here, E2, E3, 2, that is process 3. Event 2 of process P3 is moving to event 3 of process P2. This is happening in the past. So that is not a problem. It is an inconsistent cut. It is an consistent cut. Then look at process P3, E3. That is event 3 of process P3 is moving to event 2 of process P4. This is also, both are in the left side of the cut. So they are also consistent cut. Then which one is inconsistent over here? When you look at the first one, P1, okay, event 2 of process P1, where is it? It is in the right side, it is in the future. But when it is going, where is it going? It is going to P2. P2, that is event 2 of process P2. So from future, it is going to the past. Is it possible to go from future? Then there should be some sort of time traveling. It is not possible. So here we can say that C1 is an inconsistent cut. But if you look at C2, there are only two cases in that if you want to check. For event 4 of process P2 is in the past and it is going to event 3 of process P1, which is in the future. That is possible. Then the other one is event 4 of process P1 is going to event 5 of process P3. So they both are happening in the future. That is not a problem. So we can say that C2 is consistent. That is what here it is, they have explained it in detail. And why we are using this cuts in space-time diagram, because it provides a powerful graphical aid in representing and reasoning about global states of a computation. And this is about consistent and inconsistent, which we have discussed. Then we have past and future counts of an event. We'll tell that with an example. I have already told that, but I'll tell you once again. Do you remember this example where you wake up? Okay, you wake up, you get ready, you go to your college, you start have your assignments to submit, you go visit the faculties or teachers. So here I'm telling what is the past of going to college. What happens before going to college? You have to wake up, then you have to get ready. So these are the two past events that happened, or the past cones of the event. What are the future cones? You went to the college, you submitted your assignments, you met your faculties. That is future cones of the event. So if we want to say that an event EJ, it can be affected only when, that is only because you wake up in the morning and you got ready, you went to college. You can't go to college without waking up or without getting ready. You can't submit the assignment without going to the college. So everything, it happens in a linear order. Only because the first thing happened, the second thing happens. That is only when a event EI occurs, EJ can occur. And all the information which is available at EI should be accessible to EJ also. That is past of an event, the past cone. Similarly, you have future cone of the event also, just like how I have told you right now. Then we have models of process communication. Models of process communication we have already learned. This video is something which we have already learned. We are revising those things. It's mostly like that same repetition of the previous things which we have learned before. Synchronous and asynchronous. We know what synchronous is. Synchronous means when a sender sends a message to the receiver and it will wait until it gets a response, or until the receiver receives the process or receives the message, waiting till that much of time. Example, you send the message to your friend through WhatsApp and you will be waiting for him or her to receive the message and give you a reply. That is synchronous communication. Whereas in asynchronous communication is something where you send the message and then you continue doing your work, you study or you continue doing your work. You're not waiting for that message to for that person to receive the message or for that person to give you a reply back. That is asynchronous communication model. Then some of the differences inside it is synchronous communication can be blocking and asynchronous is non-blocking. In synchronous communication, the sender will wait, but in synchronous communication, the sender will continue doing its work immediately. Synchronous communication, what is required? Synchronization is required, but in asynchronous, this synchronization is not required. And in synchronous, there is no complex buffering, but in asynchronous, buffering is required. Synchronous is easy to implement and also parallelism is lower and therefore it has low performance. Why parallelism is over? Only when it gets a response, it will continue. Until that much time, it will be idle. And this is more prone to deadlock. Synchronous communication is more prone to deadlock. Whereas asynchronous communication is more complex and it has higher parallelism because it is not waiting for anyone. Once it sends a message, it starts doing its next work. So it has higher parallelism and it also has better performance because it is doing its work efficiently. It is not waiting for anything. It is less blocking, but it is hard to verify. So that is about models of process communication. And that is the end of module 1. If you have any doubts in these sessions which we have discussed, there are 7 parts. If you have any doubts in any of the videos, please ask it in the comment section. We will come up with the next module soon. Till then, bye bye.